All right, lesson 4.5 is curve sketching. On our first page here, the very first step is to determine any discontinuities or limitations on the x values. If there are any discontinuities, investigate them on either side. Determine the vertical asymptotes. That is a very similar step there in itself. Now, for discontinuities, we're usually looking at a rational function. Let's go over to our second page here, and we're going to zoom in a little. We don't have a rational function. We have a polynomial here, just a function. Okay, so we don't really have any vertical asymptotes. We don't have to worry about that. This is going to be a continuous function all the way through. Nothing's going to cut it off. Step 2, vertical asymptotes, done. Step 3, determine any intercepts x and y. Okay, well, x-intercepts are when y equals 0, and y-intercepts are when x equals 0. Okay? Well, I can quickly find my y-intercept. I know that when x is 0, y is going to be 0. So I have that one right off the bat. That's very simple. X-intercepts, though, we got to put f at x equal to 0. In other words, we're going to have to factor this equation here. So I'm going to factor f at x is equal to, I can take x out of everything, so I get negative 3x squared minus 2x plus 5. Then we're going to try to factor this part of the equation here. I'm going to look for factors of the first term. Well, that's just negative 3x. Or actually, sorry, I do like factoring out the negative. So I'm going to factor out the negative. I only like working with positive when factoring. So we're left with negative x, that's positive, is now 3x minus 2 plus 2x minus 5. Factors of the first term are 3x and 1x. Factors of our last term are 1 and 5. So we know we're going to be using those. Their product needs to add up to our middle term, which is positive 2x. When I multiply across, this will give me 3x and 5x. Well, the 5 will need to be positive and the 3 will need to be negative. In other words, when I multiplied by that 1 now needs to be a negative term. So we're left with negative x and our two brackets. In one of the brackets we put 3x, in the other bracket we put 1x. And because I multiplied 3x by negative 1, they go in opposite brackets. And because I multiplied 1x by positive 5, they go in opposite brackets. Okay. So our factor form of f at x is equal to negative x, 3x plus 5, x minus 1. Remember, we're looking for x-intercepts. So that's when f at x is 0. So in order to make 0, I have three terms here. I'm going to set each of them equal to 0. Negative x equals 0. 3x minus 5 equals 0. And x minus 1 equals 0. I've split this into three types of 0. Because if any of these three were to equal 0, we know it would equal 0 in the end. Well, that gives me x is 0. X is 5 over 3. And x is 1. I have three x-intercepts. Or in other words, my x-intercepts are, remember this is when y is 0, 0 and 0. We already knew that for a y-intercept. 5 and 3 and 0. And again, 1 and 0. So those are all major points. Yep. This one? When the 5 comes over, it becomes positive.
No, but in the first one.
Oh, you're right. It was positive. So this becomes negative. Okay, thank you. There you go. So negative 5 over 3. Okay, so we have our critical points. I'm going to highlight all these critical points. We'll zoom out a little. All of our critical points here. We have our y-intercept at 0 and 0, and we have our x-intercepts at 0 and 0. We knew that. Negative 5, 3 and 0, and 1 and 0. So let's actually make a graph here. Okay. Remember our critical points, or sorry, our intercepts were at 0 and 0, 1 and 0, and negative 3 over negative 5 over 3. So that's like 1 and a bit. So we're crossing the x-axis at all three of those points. We've got that. So let's jump back to our original page of instructions. So we've checked for 1, checked for 2, finished 3. Determine any critical values by finding f prime x, where f at x, or where f at x is undefined. Again, we're not going to have our undefineds here. So what we're going to be looking for is when our slopes are 0, or critical values. So let's go over again. We'll put a new page in between this. So we're going to have to derive our function. Our original function being f at x is equal to negative 3x cubed minus 2x squared plus 5x. We need to derive this. So f prime x is equal to negative 9x squared minus 4x. Oh, sorry, that was 5x, right? Plus 5. So we now have a quadratic. Critical values occur when f prime x is equal to 0. So we set this equal to 0. I look at it. I am not going to be able to factor this through our normal style of factoring. I'm going to have to use what formula? Quadratic formula. So I put in our quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. Recall this is our a value, b value, c value. Plug these into our equation. X is equal to negative b, well, is negative 4, so we get positive 4 plus or minus the square root of b is negative 4, squared will give us 16. Negative 4 times negative 9 is positive 36 times 5. 36 times 5, 180. So plus 180. All over 2 times a, well, a is negative 9. 2 times negative 9 is negative 18. Okay. X is equal to 4 plus or minus the root of 196 divided by negative 18. Again, that's going to split. X is equal to 4 plus root 196 over negative 18. And x equals 4 minus root 196 over negative 18. We're going to end up at values of x is 1 and x is 5 over 9. You know what? I think I could have factored that. Oh well. This is what we got. So 1 and 5 over 9. We've done that. Those are our critical values. Okay? Now, I'm going to draw on that graph we had. I'm going to draw lines through these points just because our critical values here, sorry, what were they again? 5 over 9 and x at 1. Sorry, negative 1. And these might be vice versa. So at negative 1, I'm going to put a line through it just so we have an idea. Now, it doesn't mean it's a vertical asymptote. I'm going to do the line in a light blue. So we have 1 at negative 1. So that's going to be a critical, a turning point. And the other one is at 5 over 9, which is somewhere like that, in between those two. So those are going to be turning points. So far what we have found is x-intercepts and a y-intercept and 2 major turning points. Okay, so we have that much information. Yeah, you probably could have. It would have been easier to factor. Okay, so we found any critical values. Determining intervals of increase and decrease. Well, that's when we take our derivative and we find values around those critical values. We find out when we're approaching the critical value from left and from right. So let's go back to our critical values. These were our two critical values. So let's talk about the function when f prime x is when x is less than -1. Okay, we're going to find a value for f prime x, and it'll tell us something about the original. We're going to find out when x is between -1 and 5/9, and then again when x is greater than 5/9. We're going to plug those values into our derivative function. So think of less than -1, maybe we'll plug in the value of -2. Okay? And see if we get a positive or negative value. We plug -2 into our derivative. -2, this becomes positive. Oh, we're actually going to have to find the values. This will become +4, -36 plus 8 plus 5. We're going to get a negative value. So if f prime x, when less than -1 is negative, we have decreasing. Okay, so that means our graph is coming downwards. In between, we're going to use something like, no, 0 won't work for us, because we know that. Think of it like 0.5, okay, or a half. So use a value like a half. Well, if I put a half in and I square it, it's going to be a little harder to do. If I put a half in here, a half squared is a quarter, so we get -9/4. A half times 4 gives us -2 plus 5. This will give us a positive answer, okay, when we look through it. So our derivative positive, that means it's going to be increasing. And finally, greater than 5/9, we'll think of the value 1. If we plug the number 1 into here, we're going to get -9 minus 4 plus 5. We get another negative answer, which means it's decreasing again. Okay? So we're decreasing again. We figured out that information. We'll go over to our graph. We know we have something now that's decreasing to start. Okay? Cuts through here. We can find out what the critical value is. It's going to come up, flip again, and then head back down. Okay? But what we really do need to find is when things are concave up and down. That's essentially the last thing we're probably going to have to look for here. Look down this list. We found determine intervals of increasing and test critical points to see if there are local maximums or minimums. Okay, we can find out local maximum. Horizontal asymptotes, we won't have any. So we've checked those two also. Determine f prime x for inflection using intervals of concavity, and then sketch. So the last thing we need to do is find second derivative of this function. Okay. The original function said, again, f at x was equal to -3x cubed minus 2x squared plus 5x. The derivative, -9x squared minus 4x plus 5. The second derivative, -18x minus 4 is our second derivative. Okay. We need to find our point of inflection. If there is one, that's when f prime x would be equal to 0. Okay. So we set that equal to 0. We get 0 minus 18x minus 4. We bring the 4 over. 4, 18x. Point of inflection is at 4 divided by -18, which is roughly -0.2. Okay? To prove if it's at a point of inflection, we have to see if concavity changes. If you guys remember. Now remember, we had critical points around this. We had a critical point at -1. Okay? We had a critical point. Let's kind of zoom out a little. I'm going to make a small graph of what our critical points were. Remember, we had a critical point at -1, another one at like 5/9. Okay? We had an x-intercept here. And we knew that this graph was doing something where it came up, critical point here, and it comes down. We know its inflection now is at negative 0.2. So inflection happens here. That means if it is inflecting, we're changing from concave up to concave down after that. And we do have to check this. We have to check for a point in between these, or at least to the left of negative 0.2. So something like negative 0.5. And to the right of 0.2, something like 0.5. And we have to plug them into our f double prime x to find if it's concave up or down. Well, f double prime x here is negative 18x minus 4. If we have negative 0.5 as one value and 0.5 is our other, okay, to find out concavity around it, double prime negative 0.5 gives us negative 18 times a half gives us positive 9 minus 4, 5. Positive. Therefore, concave up. And f double prime at 0.5 is equal to 0.5 times negative 18 is negative 9 minus 4, negative. Concave down. So because it changes from being concave up to concave down, we do have a point of inflection at negative 0.2. So let's jump to our graph. I'll try to zoom in a bit if I guess I can here. A little too much. Okay. At negative 0.2, so somewhere along here, we have our point of inflection. Okay. So remember, this is a rough sketch of our graph. It's going to come down, cross the x-axis here, turn, cross the x-axis here, change its inflection, turn, come down again. So that's where that black line is where it inflects, goes from being concave up to concave down. If we'd zoomed in a little better, it might have been nicer. Okay. This is where it's important. We flip from being concave up to concave down there.